The question that I have is, could you review the definition of stress relevant to soil analysis? Remember we talked about Tesagi's effective stress principle, right? As part of that, we talked about vertical stress and the horizontal stress. These are actually normal stresses acting normal to these planes. We didn't talk about shear stresses. But if I take my point within an embankment like this and define a differential element with respect to the horizontal and vertical directions, then there will be a shear stress on these planes. So let's define these stresses properly first. Here is a description of the 2D stress. First of all, we should note that when we talk about a stress at a certain point, we are not talking about a scalar like density at a certain point. We are talking about more than one component of the stress at that point. So what I have done here is I have defined a two-dimensional differential element with respect to the two-dimensional Cartesian coordinate system xy and marked the stresses on its faces. So we have normal stresses and shear stresses. Just for the sake of this discussion, I'm going to call these planes as follows. X-plane means a plane normal to the x-axis, and similarly this will be the y-plane because that plane is normal to the y-axis. Then this is how you interpret the subscripts we use with a stress component. Sigma xy means stress in the x direction on the y-plane. For example, this shear stress component, right? This is acting on the y-plane but in the x direction, and therefore we are calling it sigma xy. Similarly, this will be sigma yx, and of course this will be sigma yy because it is acting in the y direction and acting on the y-plane. I'm not going to go through the derivations here, but it can be shown that sigma xy equals sigma yx. These are what are called the complementary shear stresses. And therefore, there are only three independent stress components in this picture here: sigma xx, sigma yy, and sigma xy. And we commonly put this in a matrix, in a two-dimensional matrix like this. So we have the normal stresses on the diagonal terms and the shear stresses on the off-diagonal terms. Because the off-diagonal terms are equal to each other, this matrix is a symmetric matrix. We won't do much with the 3D stresses, but just for completeness, let me define that here as well. So this 2D matrix becomes a three-dimensional matrix. This 3D stress is symmetric as well. But had this not been symmetric, we would need 9 different components to define this stress matrix. If you recall, displacement is a vector, right? Velocity is a vector, right? To define a displacement vector in general, we would need 3 components. But to define a stress, we need 9 components. These are all what are called tensors. Displacement is a first-order tensor. Stress is a second-order tensor. First-order tensors require 3 components to define them properly, and second-order tensors need 9 components to define them properly in general, of course. Here are the 3 types of two-dimensional approximations: plane strain, plane stress, and axi-symmetric. In the plane strain and plane stress problems, the stress and strain components in the xy plane vary. The shear components involving z are 0 in both cases. The main difference between the plane strain and plane stress approximation is that in the plane strain approximation, strain in the third direction, which is the direction perpendicular to the paper, remains a constant, which renders the stress in that direction to vary. Whereas in the plane stress problem, the stress in the third direction remains a constant, which makes the strain in that direction to vary. In the axi-symmetric problem, the loading boundary conditions and material properties are symmetric about the axis. The stresses and the strains vary in the R-Z plane. The shear components involving theta, the hoop direction, are all zero. In addition to that, the hoop stress and the strain vary during the loading. So consequently, we have four non-zero components of stresses and strains in the axisymmetric problem. If you have a long concrete dam where the cross-section does not change along the length of the dam, then the plane strain approximation is usually appropriate. If you have an axisymmetric pile foundation or a shallow foundation, then the axisymmetric approximation is appropriate. You may be wondering as to how the Tesagi's effective stress principle applies to problems involving shear stresses. It turns out that the shear stresses are not affected by the presence of the pore water pressure like shown over here.